Well, welcome everyone to today's CFEGA Lunch and Learn webinar, Packing Shed Sanitation and the Use of ATP Swabbing to Aid in Sanitation Decision Making. I'm Adrian Card with the Colorado Fruit and Vegetable Growers Association, and I'll be your host for today's webinar. Today's webinar is intended to help you understand 5 key concepts in packing house sanitation and best practices when implementing and using an ATP meter and wet sanitation practices. CFEGA is the go-to resource for Colorado's fresh fruit and vegetable farmers. We connect Colorado growers with industry, government, academia, and consumers to strengthen and expand Colorado fresh fruit and vegetable production. Learn more at coloradoproduce.org, Facebook, and Instagram accounts. CFEGA would like to thank its sponsors, learn more about these businesses that support the Colorado produce sector by, let these slides advance here, by visiting coloradoproduce.org and click on the Growers tab and the menu and select Find Products and Services. And you can see a directory of all of these various vendors and services and products they can offer you. I know many of you have deep experiences in Zoom webinar, but just to point out, we will be using the Q&A box that you see on your toolbar for questions, and I'll moderate that for our presenter today. And you can resize Zoom to make it fit whatever size monitor works best for you. And look for polls. We'll have 2 polls, one at the beginning, one at the end. And speaking of, let's go ahead and get started with our first poll before I introduce our presenter. So tell me, how familiar are you with ATP swabbing as a sanitation management tool? Are you very familiar, somewhat familiar, not very familiar? I've never heard of ATP swabbing. So looks like we've got of our respondents here, Eduardo, let me show you here. A little bit across the board. Everybody has some experience with it. So that's good. We've got a starting point for today's presentation. And without further ado, let me introduce to you Dr. Eduardo Gutierrez-Rodriguez. He's an assistant professor in food safety systems in the Department of Horticulture and Landscape Architecture at Colorado State University. Dr. Gutierrez-Rodriguez has over 20 years of research, extension, and business experience in food safety, focusing on fresh produce and minimally processed food environments. And with that, Eduardo, I'll pass over to you.
Welcome to everybody. I have a little bit of cough here I'm trying to get rid of, so my apologies if I sound a little bit winded here. I'm going to share my presentation with you here today. And like Adam was saying, the goal is to touch base a little bit on packing shed sanitation and ATP testing, okay? So I want to frame us all as to why are we here and where are we are. So today we're going to focus on 3 main aspects within the produce safety rule. One of them is that it requires either open or closed facilities to have adequate design, construction, and workmanship. I get a lot of questions about what is adequate design and construction. So I pulled out some information from FDA that really talks about adequate design and construction and how that impacts cleanliness and proper maintenance. And specifically, when we're talking about food contact surfaces, how this is going to impact cleanliness. And as we're talking about cleanliness, then we're going to try to tie this thing with the use of ATP as one of those startup points when we're looking into efficacy of sanitation and cleanliness procedures. And of course, that is going to sort of give us a little bit of an example of how that is going to impact how easily it is to maintain and how easy it is for us to be able to clean or maintain sanitary operations, which are basically 3 of the key requirements within Chapter 6 of the packing house aspects of the produce safety rule. Of course, there are some facilities, excuse me, some operations that are also considered facilities. And what I mean by that is that they also have to meet the preventive controls for human food. And in those areas, then the way it's tied is because preventive controls for human food, environmental monitoring becomes an important aspect in the system. And ATP, besides microbiological testing, could be an important tool within the environmental monitoring plan. So if we're thinking about packing house flow diagram, our goal is to basically have a linear flow in which we have a dirty area or a dirty zone here and a clean area around this area. And so the goal is to be able to condense or compartmentalize the amount of residues that are moving in this direction, okay? Because when we get to the washing aspect of things, and when we get to the packing aspect of things, the amount of cleanliness that we have in those areas may impact also the type of results that we have within an environmental monitoring plan. And so we were to put this in a simple process flow, then we will have an incline elevator that goes into a washing machine. Then we have some sort of sorting and peeling going on, slicing, then some sort of blanching, depending on the operation that you might have. This blanching could be gone, and instead of this, we could go straight into spinning and then drying the product and then putting it back into boxes. And so the question that is always asked is, when we're looking at cleanliness, what zones do we swab? How do we go about this process? And so today, hopefully, we're going to be able to address a little bit that from the standpoint of ATP. Just to remind everybody, we have 4 basic zones that are associated with contact surfaces. Some of these will be food contact surfaces. Some of these are not. So zone 1, of course, will be that will be in direct contact with the produce, and that will be our food contact surfaces. Then zone 3 and zone 4 are zones that are away, either offices, zone 4, floors, legs, or in between. That doesn't mean that those cannot be part of our environmental assessment. And in many cases, floors, drains, and legs could be a significant source of contamination for zones 2, which are adjacent to zone 1, or to even zone 1 that will be food contact surfaces. So one of the questions that we always get asked is, where do we start? What kind of systems are we going to use to evaluate how good our sanitation procedure is? And so later on in the presentation, we're going to address this a little bit more in detail. But we need to think of hazards. And of course, we have microbiological hazards, typically in environmental aspects, either Listeria monocytogenes, Salmonella, or pathogenic E. coli are some of the ones that we're looking for. Mainly, Listeria monocytogenes is one of those that is the most important. Then when we're thinking about chemicals, in most cases, we might not be able to have allergens, but the addition of chemical sanitizers, the addition of lubricants tend to be some of the most significant interfering aspects that we have when we're doing a proper environmental assessment, and that interfere either in ATP analysis or that interfere into our own microbiological analysis. And specifically for microbiological analysis, we could be thinking of any of these 3 pathogens, or we could be looking at indicator organisms of the presence of any of these 3 pathogens, okay? So that's thinking of the hazards within the packing house. So when we talked about zones, like I said before, we have food contact surfaces that are zone 1, and then non-food contact surfaces that tend to be zones 3 and 4, and in some cases, zones 2. And if we want to tie that back to the construction and design of equipment and the requirements that come from the product safety rule, one of them is that they will be of adequate design. And so if we think about them, the general criteria provided by FDA is that they need to be smooth, impervious, free of crack and crevices, non-porous, non-absorbent, non-contaminating. This is one of those that is, we can put a lot of signs there, non-reactive, corrosion resistant, and then easy to clean. So 2 quick examples here. If we think of metals, we have stainless steel, and we have these options. We have 303, 304, 316, and 318. And basically, just by the amount of nickel or chromium that is going to be in that stainless steel, is what is going to impact each of these numbers here that we have here. The highest chromium and nickel contents are typically in the 318, and therefore we have a smooth surface that is impervious, that has almost no cracking, and therefore is non-reactive and less corrosive. So what we see many times is that when we go to facilities, we have stainless steels that are from lower grades, and therefore pitting, shaving, cracking, or things like that happen. And this happens in stainless steel specifically because the amount of nickel and chromium in those type of stainless steel is much lower, and therefore it is more susceptible to the type of antimicrobials that we use in facilities. Excuse me. If we're talking about plastics, here I gave you an example of the typical ones that we might have in a conveyor belt, or that we might have in cutting tables, or that we might have in other aspects in the conveyor belt. And so basically, they are different plastics that can respond differently to the sanitizers, and the level of the smoothness and porosity will basically change based on the standard of plastic that we're using, okay? Smoother, less porous will be these ones, more porous or less smooth will be these other ones. And why we're talking about this is because when we do ATP measurements, the values that we typically get for metals will be very different than the values that we get from plastics. And so one of the typical common mistakes that I see is that we use identical ATP measurements for both materials. And so one of the things that I want to make sure that is clear to all of you is that we can have different parameters, different ATP values, either for metals or for plastics. One of the other aspects that we take into account besides those aspects is whether they are corrosion resistance, and if they are free from flaking or shipping, or if we have welding. And so what we see in many of these low-grade metals is that we can see a lot of this flaking going on, or we have a lot of this pitting, and we find a lot of welding that is not food grade, like this example that we have here. And so therefore, it is very easy for microorganisms to attach to these surfaces. And if I am doing ATP measurements or swabbing, the value that I would get in an ATP measurement here, it is going to be different than the measurement that I have here. And so what I see typically in many instances is that these differences are not being introduced into the swabbing protocol, and you see a lot of variations going on into these measurements. And so if you're using the ATP or the microbiological testing for pass, no pass, or pass-fail scenarios, just by swabbing the wrong area or by having the wrong characteristics of the materials, you might not ever be able to comply with those pass-fail requirements, okay? And I'm gonna get a little bit more in detail as we move forward in the presentation. So when we talk about construction and fabrication, what I try to use is basically information coming directly from FDA that talks specifically about what is acceptable and what is unacceptable, because we hear about acceptable designs, but we are not told exactly what are those acceptable designs. So if we talk about what is acceptable, we want to make sure that they are free of sharp corners or crevices. So in this example for drains, what we want to see is a drain that has a specific inclination, and drains that don't have any false floors like this one here that will allow for things to accumulate here on these sides. Okay, so when we're talking about drains or surfaces, those are some of the aspects that we're considering to be of adequate design, meaning there is no sharp corners and there are no areas where the product or where liquids or where other products can accumulate in the system. And one of them is in drain design. And if we have a system like this, then it is pretty easy for a biofilm to produce. And then that biofilm basically is going to start going up, and it's going to start growing up. And so if we are treating this, and then we have the typical crate that we have here, then this biofilm can actually come out and start contaminating these zones in which we're moving around. And so something as simple as that can create a lot of mayhem in facilities. When I was in the industry, unfortunately, This was the type of drain that was in our facility. And we had a listeria problem that in some instances was associated with the poor draining design that we had in that facility. Had we had, excuse me, something like this in which there is no areas for accumulation, this biofilm should have not been formed. So if we talk also about CIP systems, clean in place systems, right? Which is different that we are basically bringing materials to clean in that area, or we are treating these materials in that specific location. We need to be able to have our ability to prevent these centric and concentric areas, because here is where all the accumulation of the product is going to happen. And therefore, if we're going to try to treat this with any kind of residues, then in these areas here, or in this corner here, is where all the accumulation is going to happen. So we need to make sure that they are in a certain inclination, okay? And there is a specific values associated with these pipes that prevent that specific accumulation and that permit a specific controls, not only to prevent accumulation of the liquid, but also to prevent accumulation of the sanitizers. Another example that I see all the time is when I see how a wall and the floor connect to each other. In many instances, we see this. And if I want to find a microorganism, I go and swab basically that area. That is where they are all going to be. So what it is considered adequate design is basically one that has angles or internal angles of 135 degrees or less. So in that way, anytime there is proper sanitation going on, there is less likely for anything to be accumulating here, okay? And of course, if we're going to swab any of these areas, being able to find something here versus here is going to be significantly different. Another aspect that I see constantly is welding. And in welding, sanitation, food grade sanitation or food welding, it is critical. I showed you an example before in which we had this lap welding going on, and this is paradise. This is where I can go and find any kind of organism. And if I have a swabbing system and I have not trained my individuals to actually either treat sample here or sample here or sample here, if somebody then goes and combines all these, the level or the measurement that I'm going to get is quite different. So one of the key aspects when we're doing these type of swabbing systems is to be able to validate each area that we're going to swab and to be specific to the area that we're trying to analyze, okay? And again, we're gonna get into this a little bit more, but the important part is to be able to have food grade type of welding to prevent these accumulations that not only are going to allow for biofilm formation, but they're also going to interfere in our ability to be able to do a proper assessment of cleaning of a location, especially if you have not defined specifically which areas you need to swab. So here's just another example of what kind of curvature we want to have based on the union of locations. And so remind ourselves that here, the goal is to have 135 degrees or less angle to be able to have proper inclination and prevention of accumulation and biofilm formation that would happen around here, okay? Another aspect that we get asked a lot, and this is specifically when we have tables and when we ask like, how do you swab a table? Many of the I would call it the older designs have this type of ends to the table. Basically, there is a lot of accumulation that can happen here. Sanitation comes, they try to clean everything else perfectly. A lot of the residues come here, and then these biofilms start forming, which then allows it to literally creep up and come back up very easily. Or we have this other design in which it allows for it to be the same. So what it is considered acceptable is that the end of the table is either closed or that it is in this angle, so that then there is the ability for everything to drain down and prevent the accumulation of any residues and therefore the formation of any kind of biofilm in that room, okay? So that is how the design of the table at the end of the tables should be with any of these three designs. What we find out there is that some of the cheaper tables with cheaper stainless steel materials have all these problems here and therefore become a problem later on when you're trying to evaluate your system. Okay, so we've been talking a little bit about biofilms, and so I just wanted to quickly remind everybody how this happens. An organism comes in, starts and creates these polysaccharides. As it creates more polysaccharides, more organisms begin joining. These organisms begin to multiply, and at the end, it forms this kind of mature biofilm that is kind of divided in two sections. This section is the section that flies away and that continues to contaminate our products. This section, we would call this a section of resistance that prevents many of the sanitizers from coming in, and that there is a lot of antimicrobial resistance associated in that area. And here, it is where everything was originated and that it is much more well attached to the surface. So if we don't have a smooth surface, or if we don't have the best design, what typically happens in a sanitation process is that we are only able to get rid of this part here, of the top part, and everything else remains the same. And so when we're doing this, then of course we're going to have poor sanitation also, but then we're not going to have consistent ATP or microbiological readings because there's always going to be residues left on the surfaces of the tables. When we talked about those biofilms, then of course they're going to be benefited by what? By the type of material that we're using. So here is a cheap stainless steel that corroded pretty easily, and now you're creating all this pitting and debris going on that then of course allows for the microorganisms to stay. Of course, there could be poor design like this one, in which you won't be able to clean any of these rolls that you see here. And so then the question is, have I cleaned these well? If I use an ATP or if I use a swab, how do I know if I have been able to clean every one of those areas correctly? And the answer is, you're never going to be able to know. And so this is how the design of the facility can significantly impact your ability to know whether a system is really well cleaned and sanitized, okay? So when we're going to test food contact surfaces, there's basically two approaches. One in which we're focusing on ATP testing, and we're going to talk about specifically about what is ATP. And then another one in which we're basically focusing on microbiological analysis. And Rodak plates is just an example of how you can do this microbiological analysis, but you can also be doing some swabbing like this one, or some swabbing like this one. The key aspect here is that baby steps and making sure that you are going step by step in the process. So what is the best practice? The best practice is first to start by listing all the equipment that you have. Once you have identified all the equipment, then identify that equipment by zone. Zone 1, Zone 2, Zone 3, Zone 4. And then once you've done that, start with ATP. Why? Because in ATP, what you're trying to measure is residues of organic matter. You can ask or use this ATP even in Zone 1, and it's not going to trigger a positive test for a human pathogen that then you need to address at the time. What I see most of the time is that people go directly into these microbiological swabbings. They start testing for many microorganisms, and then they find themselves in trouble. If you start with an ATP system first, in which you're trying to look at how much or how efficient your sanitation system is, this is going to tell you how much residues may be left in each of the surfaces that you're doing, and to establish pass and fail criteria for ATP that then you later verify with microbiology. How do you verify the microbiology? The most important part, or the first step for verifying in microbiology, is to do indicator organisms, not specific human pathogens. So if you do Enterobacteriaceae organisms like this, then Enterobacteriaceae organisms are basically targeting gram-negative organisms. And which are those? We're targeting Salmonella and we're targeting E. coli, the pathogenic E. coli. Aerobic plate count will be a measurement that is much more specific to the overall population of organisms that you might have there. The understanding is that you have proper cleaning and sanitation, the concentration of this aerobic plate count is going to be very low. And even more low is going to be the concentration of Enterobacteriaceae organisms. Okay, so how would you know? So if you were to do APC, aerobic plate count, as a verification activity first, APC means all the organisms that could be there. And then you decide to do Enterobacteriaceae organisms, for example, the results of this will be populations much higher on APC, aerobic plate counts, and populations much more smaller on Enterobacteriaceae organisms. So basically, APC will be all the swimming pool of organisms, and Enterobacteriaceae will be a much smaller pool of organisms. And then Salmonella and E. coli will be even a smaller group down here. So those two will help us to verify whether our ATP measurements are allowing us to determine that we have low organic matter and at the same time, low microbial residues. And the best way to start this is by doing indicator organisms. Which indicator organisms? Either aerobic plate count or Enterobacteriaceae. For dry packing house environments, for dry scenarios, sometimes yeast and molds, it's important and could be an indicator too. But for dry packing house environments in which we are not able to really do a deep clean and deep sanitation, the use of ATP or the use of yeast and molds is a little bit cumbersome. Okay, so today what I'm going to do is focus on wet sanitation procedures and how we can use ATP and aerobic plate counts and Enterobacteriaceae as a way to identify how good our cleaning and sanitation procedures are going. So what is ATP? Basically is a molecule called adenosine triphosphate. And this molecule is found in all animals, in all plants, in all microbial cells. It is an indicator of organic matter. I want to repeat that. It's an indicator of organic matter. And the idea is that if we have low organic matter, most likely, we're going to have low microorganisms. Most likely, we're going to have low microorganisms. So how do we measure ATP? This is an example of how we measure ATP. This is an ATP meter. It doesn't matter the brand, but the key part is how you're doing the swab and what area are you swabbing, okay? And this ATP is measured basically in these units that are called relative light units. And so how these units relate to organic matter is basically in this way. If you have high RLUs, then you're gonna have high ATP measurements and therefore you're gonna have high organic matter. That's where you find yourself. If you have low RLU units, then it means you're gonna have low ATP and therefore you're gonna have low organic matter, okay? And the goal is to be as low as we can in this area to be able to have less likelihood of us having organic matter and the potential of a presence of organisms. One thing that is important to make sure is that every company that sells ATP meters has a different RLU value or a different RLU standard for pass or fail limits, okay? So when you buy one of these machines, you need to make sure that you understand what are those specific parameters that are being given by the manufacturer of the company, okay? Now, here's an example of different brands. Here's a Hygiena, here's a Neogen, here's a Charm, here's a Biocontrol, and here's a 3M. The goal of this slide is to basically show you that each of them has different components. And why is that important? Because some are easier to handle than others. And so you need to make sure that you familiarize yourself and that you train the individuals on the proper use of each of these swabs. What do we use ATP for? To validate cleanliness, to validate the cleanliness of new equipment, to clean or train in, to train in cleaning and sanitation procedures, to potentially identify risks of contamination. But one of the misconceptions is that this can also be used for the control of allergens and microbiology, and that is not true. It is not used for allergen control, and it has to be supported by an additional microbiological test to be able to get us a better understanding of the cleanliness of that surface, okay? So what are some of the key issues that I see all the time? First is understanding your ATP system. Each of them, has a different way of measuring, has a different time interval, has a different calibration method, and so you need to be able to do that. One of the biggest mistakes that I see is in the way swabbing is done. So here is an example of how swabbing should happen. Basically in this direction, then in the opposite direction, and then across on each of the sides. And so that is what it would be considered a proper swabbing aspect. One of the other things that I see all the time is that you really need to bend your swab to properly be able to extract some of those residues from the surface. I see a lot of people doing this, and therefore you're going to have different results. The results are actually going to change a lot. One of the other issues that I see is that many people are not using any calibration ones or any positive controls in the units. So they've been using them forever. They don't know if they're reading exactly, and we don't know exactly how much controls are you getting in these unit measurements. So if you buy a system, please make sure that you have these calibration controls and these positive controls. We talked a little bit about proper swabbing. And the other thing that is important is determining which of the areas need to swab, what is the frequency of swabbing, and how many swabs do we need to take. And we're gonna get there in the next slide here. But one of the things that is key is that not all these areas need to be swabbed identically. And one of the other mistakes that I see is that sometimes they take the sample and it takes forever for them to put it in the luminometer to measure the ATP measurement. So the best practice is that you do this in less than 1 minute, okay? But it's going to depend also on the type of machine that you're using. So let's get a little bit into how many swabs, what's the frequency, which is some of the things that you probably are going to be looking for. If you have regular surfaces, the recommended swabbing area is a 10 by 10 centimeter area. If you have irregular surfaces, training for each surface is specific, and that is going to be given by how representative your measurements for ATP are. So what you need to start is by basically trial and error, trying to make sure that you know that the sanitation is going correctly, and at the same time that you're doing accurate swabbing of the area. You need to train everybody to make sure that there is consistency in swabbing, okay? And also trying to prevent as much as possible cross-contamination between areas. Because if your goal in this example is to swab the interior and somebody swabs the exterior, then the measurement can be completely different. And so in these irregular surfaces is where I see the biggest variability and many issues with pass and fail values, not because there is a problem in sanitation, but because there is a problem in the training of how each area should be swabbed. So what are the best practices? So as you can see here, we have a conveyor belt. And so we can have two areas. This is zone 1. And here we have zones 2, okay? Zones 2. And so what we need to do is define the number of swabs per location so that we can consider this clean and satisfactory, okay? And use microbiology as confirmation. So how do we go about that? Typically, to do validation of this, you need to take between 5 and 10 swabs per location. And do this in multiple sanitation events, okay? At least 3 separate occasions. So at least in 3 separate sanitation steps. So you do a sanitation step, you swab a specific area 5 or 10 times, you recover the data, and then you repeat that 3 more times. And then once you've done that, then you can calculate what is the variability within the system. And I have a little bit of an example here in the next slide, because then we need to define what is going to be the average, the standard deviation, and the standard error that you're going to have for each specific area that you're swabbing. And the pass and fail values are going to be based on each of those units. So here's an example for this swabbing area. We have 4 locations. We're going to do 5 measurements per location, and we're going to have 3 independent washing events. What do I mean by 5 measurements per location? So one of these red squares that I have here, I have zoomed it out here. So it means that this is one area that I swab. You never go back and swab the same area. You go to another area, you go to another area, you go to another area, and you go to another area. In this case, it's a flat surface. So it could be a 10 by 10 area, each of these swabs. So 10 by 10, 10 by 10, 10 by 10, 10 by 10, 10 by 10. And that represents a specific location, okay? You don't go over it. So how does this look like? So here's an example. In location one, we took 5 replicates. And so some of them had 50, some of them had 80, some of them had 30, some of them had 90. Okay. And the goal is that after you do all these 15 measurements, you're going to take an average and a standard deviation. So the average and a standard deviation for these 15 measurements is this one here, 51.8 and a standard deviation of 19.1. Okay. So that is basically going to be your pass limit criteria. If you were to just do this for one event, for this event, for example, then this would be 68. So this would be a different value. Or if you were to do it for just this other area, then the value could be lower, could be 49.6. So that's why you at least need to do this 3 times. And you need to at least take 5 samples per location to try to be able to capture all the variability that we have there. Okay. And then what we need to do is define the pass or fail limits. The pass or fail limits. So what is considered a pass limit? It is what it is considered clean. So in our case, we did 15 measurements, and those 15 measurements gave me this value. So in theory, this is our pass limit. How do I verify this? I verify this either by doing Enterobacteriaceae or by doing aerobic plate count. Okay. Now, let's define the fail limit. There's 2 ways to define the fail limit. One of them is to just multiply these values by 3. So in this case, if I multiply these values by 3, then this is what will be my fail limit. 155.4 RLUs units. This will be my fail limit. A much more conservative way of doing this is to multiply the standard deviation by 3, So which standard deviation? This one here, by 3, which is basically 57.3. And then add this value to the original average RLU that you had. So 51.8. So then the new value is 109.1. So that is a much more conservative approach. Why? Because the spread that you have between 51 and 109 is much smaller than between 51 and 155. And then your alert or operational system is anything that is in between 52 and 109 or 108. And if you find yourself in that operational limit, what it's telling you is alert, alert, I might have a problem here. How are you going to know whether you have a problem here? With the verification aspects that you do with the Enterobacteriaceae and the aerobic plate count. Okay, so that is a way or a simple way in which you can determine how efficient is your ATP system and how to establish pass and fail limits and operational limits that you can use in your facility. Of course, this is for a zone 1 example, but if you were to do this for a zone 2 example, then maybe the values will be different. And that's one thing that I want to make sure that I'm clear here. I see many times an equal ATP value for all zones, and that is not a good way to follow. So to summarize what we're trying to say, different surfaces have different levels of risks. Plastics versus stainless steel may have different ATP values, and that is okay. You need to define that based on what? The number of swabs that you do and the number of sanitation events that you do. The manufacturer may suggest to you some values. So for that specific equipment, down here, this is what the manufacturer suggests. So our measurement of 51 was basically within this value that the manufacturer gave us. But this is just for that specific example. It could be different. And the key, and the final key, is to make sure that we have significant SOPs in which we clearly describe the location, the number of swabs, the pass and fail limits, and how to swab each surface. And that's it.
Eduardo, thank you. We've got a question from Antoinette. Would you do the similar limit setting for all zones on all equipment types or mainly on zone 1? And I'm going to launch an educational poll too while you're answering that question.
So for zone 1 and for zone 2, you for sure will do it that way. If you're doing zone 3s and zone 4s, when we're talking about drains, drains is a nightmare because drains are going to be all over the place. So in the case of drains, you will follow a different approach. And in the case of drains, there are certain treatments that you are going to have to do with sanitizers and with other aspects to be able to know whether that drain is clean or not. This approach that I showed you is specifically when you're working with zone 1s and zone 2s. And this is a very simple way of trying to address how effective is your cleaning system and how you can verify this with indicator organisms that are not human pathogens. What is our concern in the food industry? Zone 1s and zone 2s, because those will be in direct contact with the crop, okay? So I would suggest to start that way and have your overall sanitation of the facility take care of the floors and take care of the drains as a separate component.
Fantastic. Other questions from attendees today? Another one from Antoinette. Can this be turned into a fact sheet that we can use to back up our decision-making for setting limits?
Thank you for giving me a homework. Yes, we can try to do that. Antoinette and others that are here. Depending on the manufacturer that you buy from, in their manual, they are going to have similar recommendations or slightly different recommendations. If you buy one that does not give you that, run away from it, because that would get you in trouble. You need to buy it from somebody that has that established already. You can even ask the manufacturer what will be the ATP levels that they consider standard for specific plastics and for specific metals. They also have that. They also have those tables and they can provide them to you. And the other mistake that I forgot to mention that I want to make sure that I don't forget is that when you do these ATP measurements, if you do them with a table that is wet, it's going to lie to you. Or if you do it with residues of sanitizers, it's also going to lie to you. So you need to let air dry, you need to drain away before, after, and then after that, you do your ATP measurement. Because if not, you're never going to meet your pass-fail standards.
Fantastic. Any further questions for Eduardo today before we adjourn? And just to mention, in case you're typing as I'm talking, today's recorded webinar will be posted to CFEGA's food safety webpage, so you can look for it there. But a lot of fantastic content today presented by Eduardo. Not seeing any other questions. So I think at that point, Eduardo, thank you so much today for making time for this. in your busy schedule. I know you're teaching, what did you say, PSR trainings for Colombians today.
Yep.
So you're an international educator. We really appreciate having you.
Thank you very much. Hopefully it helps. And you have my contact information. Reach out, and happy to help if needed. Okay.
Fantastic. Thanks, everybody. Have a great day.
Bye. Thank you.